universe has a center. You've probably imagined it before. Our universe, vast and dark, expanding outward from a single spot like ripples on a pond. It feels logical. After all, if something explodes, doesn't it burst from a center? That's how fireworks work. That's how ripples move. That's how we expect reality to behave. So, we assume there must be a central point of the universe, a location where everything began, where all matter exploded out from and still expands away from. But here's the mind-bending truth. There is no center. Not in the way you think. The Big Bang didn't happen at a point in space. It happened to space itself. Every point in the universe was once compressed together in a hot, dense state. And every point has been expanding ever since. The Big Bang wasn't an explosion in space. It was an expansion of space. Imagine a balloon with dots drawn all over it. As you inflate the balloon, each dot moves away from the others. But no matter which dot you stand on, it will feel like everything else is moving away from you. There's no single central dot, just space expanding everywhere. Now, take away the balloon's surface. Think 3 dimensions instead of 2, and realize this balloon has no outside. There's no center floating in something bigger. The universe doesn't sit inside a room. It is the room, and that room is growing. From your perspective, it might seem like we're in the middle. You look out, and galaxies retreat in every direction, but observers in distant galaxies would see the same thing. To them, we are moving away. In every frame of reference, every place looks like the center. So none of them actually are. The idea of a center works on Earth, in cities, in galaxies. It makes sense in small systems, but the cosmos doesn't follow our local instincts. It's not that the center is hidden, it's that it doesn't exist. You are not at the middle of a great cosmic balloon. You are inside something that stretches forever, not outward from a place, but outward from itself. In the quiet dark, it's strange to think. You are somewhere in the universe, but the universe is not centered around anywhere. Maybe that's why it feels infinite, because it never needed a beginning point. It only needed a direction. And maybe that's true for you, too. The universe has an edge. You might picture the universe like a giant container, an enormous sphere or a cube, floating somewhere in a larger nothingness, with stars scattered inside like confetti in a snow globe. And like any container, it must have walls, right? A place where it ends, a boundary, an edge. The human mind loves borders. It's how we've made sense of the world for as long as we've existed, where a forest ends and a field begins, where the sky touches the sea, where home becomes unfamiliar. So, we assume the universe must work the same way. But in truth, the universe, at least as we understand it, doesn't have an edge, not the kind you're thinking of. You can't travel in one direction long enough and bump into a cosmic wall labeled end of everything. There is no final stop, no border to pass through, no outside. The universe isn't a room inside something larger. It is the totality of space itself. It doesn't sit in space. It is space. And that space is expanding, not into a surrounding void, but into itself. You can think of it like this. Imagine being a tiny creature living on the surface of a balloon. To you, the surface is all there is. No matter where you walk, you never find a wall. But if someone starts to inflate the balloon, everything begins to stretch and grow. The surface expands, but not because it's getting closer to some outer edge. It's just that the space between things is increasing. Now, Take that idea and stretch it into 3 dimensions. You're no longer a dot on a balloon. You're inside a volume of space that's doing something similar, expanding everywhere at once, but not outward from a center, and not toward an edge. It's just becoming more. The observable universe, what we can actually detect, is limited. There's a horizon, a limit to how far light has had time to travel to us. And that horizon does create a kind of edge in what we can see. But that's not a true edge. It's a limit of perspective, not of existence. Beyond that boundary, space continues. More galaxies, more structure, more darkness, possibly even more surprises. And yet, even that extension doesn't imply a final wall. If the universe is finite, it may be shaped in such a way that, if you traveled long enough, you'd return to your starting point, like walking in a giant loop. If it's infinite, it simply goes on, forever, in all directions, without wrapping around. Either way, the idea of an edge becomes meaningless. There's no direction you can point where space stops. You might reach the limits of your endurance, you might run out of time, but you'll never run out of universe. And maybe that's the most quietly astonishing part, that no matter how far we look, there's always more. Not because we haven't looked hard enough, but because the universe has no interest in stopping for us. It doesn't follow the architecture of rooms and fences and maps. It just continues, silently, endlessly, indifferently, and maybe, in your quietest hours, when everything else in life feels like it's pressing in too close, it's worth remembering that the cosmos doesn't have edges. It only has expansion. Maybe that's something we can carry with us too. Space is empty. When we think of space, most of us picture a vast, cold emptiness, a black backdrop sprinkled with stars, utterly silent and still. And while that's a reasonable feeling, it's a deep misunderstanding of what space actually is, because space isn't empty, not even close. Even the most seemingly barren regions of the cosmos are filled with more than you can imagine. Let's start at the basic level. Every cubic meter of interstellar space still holds hundreds of particles, mostly hydrogen atoms, along with electrons, protons, and photons, zipping through the void at incredible speeds. That's not a lot by human standards, but it's not nothing. Even in the quietest vacuum humanity can create on Earth, space is emptier, but not truly empty. And that's just the beginning. The vacuum of space is also permeated by invisible fields, gravitational, electromagnetic, even the Higgs field. These fields are not stuff in the usual sense, but they are real. They have energy, they influence matter, and they ripple with activity. The Higgs field is what gives particles mass. The electromagnetic field lets light propagate. Gravity bends space itself, even when there is nothing. These fields are there, humming quietly in the background. And it gets stranger. According to quantum mechanics, even the most perfect vacuum isn't empty. Instead, it's full of fleeting energy fluctuations, what physicists call quantum foam. Virtual particles constantly pop in and out of existence. This energy is not theoretical. It's measurable. It explains the Casimir effect, and it's even linked to dark energy, the mysterious force accelerating the expansion of the universe. Then there's the cosmic microwave background, a faint glow of leftover light from the Big Bang. This radiation fills the entire universe, and it's everywhere. Right now, it's passing through your body, your room, your planet. You don't see it, but it's there, like a whisper from the earliest days of the cosmos. In fact, A small part of the static on old TVs came from this radiation. It's proof that space is filled with memory. Every patch of sky holds the echo of the universe's birth. So, why do we feel that space is empty? Because human senses are tuned for dense things. Air, solids, light bright enough to see. The particles and waves and fields in space are too diffuse, too subtle for us to detect unaided, but they are real. Space is not a passive backdrop. It's an active, dynamic, energetic medium, a complex stage where particles dance, light travels, gravity pulls, and time unfolds. To call it empty is like calling the ocean dry just because you're floating on a boat. Once you understand that, your image of space transforms. The silence of the cosmos becomes a symphony we're only just beginning to hear. The universe is expanding into something. When we say the universe is expanding, it's easy to imagine something ballooning outward into a bigger space, like ink spreading in water, or a firework pushing through the sky. It seems natural to ask, what is it expanding into? What's outside? But this question carries with it a misunderstanding, a deeply human one. We're used to things growing inside something else. A balloon expands into the air. A ripple spreads across a pond. A city grows across land. But the universe isn't expanding into space. It is space. To understand this, imagine you're standing on the surface of a balloon, but you're tiny, so tiny that all you can see is the curved surface stretching around you. As the balloon inflates, the surface expands, but there's no edge on the surface itself. It grows, but not into anything your two-dimensional world can access. That's a bit like our universe. The expansion isn't about galaxies rushing through existing space. It's about space itself stretching. The distance between galaxies increases not because they're flying outward like shrapnel, but because the very fabric between them is growing. And here's the mind-bending part. This happens everywhere at once. There is no central point of the expansion. Every galaxy sees every other galaxy moving away, and no one is special. This expansion doesn't need an outside, because there is no outside. As far as we know, space-time is all there is. The universe isn't sitting in a box, or a room, or a higher dimensional arena. It's not expanding into a void. The expansion is internal. It's the change in scale, not position. In that sense, asking what the universe is expanding into is a bit like asking, where is the edge of a circle? A circle doesn't have an end. It just loops back on itself. And the universe might do something similar. Or it might be infinite, with no boundary at all. Either way, the expansion doesn't push into anything. It simply is. Even more fascinating, the expansion can happen faster than the speed of light. That's because it's not matter moving through space. It's space itself changing. General relativity allows for this. It means some parts of the universe are receding from us so fast that light from them will never reach us. Not because they're far away in a place, but because they're moving away in the very structure of reality. This is why the observable universe has a horizon. Beyond it, space stretches so quickly that information simply can't catch up. So, no. The universe isn't expanding into something. There's no edge it's breaking through, no cosmic wall it's brushing up against. It's more like a story that keeps adding new pages, but the book isn't on a shelf. The book is the shelf. It holds itself. The expansion of the universe challenges our most basic intuitions. It's not like anything we experience on Earth, but that's what makes it so powerful. It reminds us that the cosmos doesn't have to fit our metaphors. Sometimes, We have to reshape our metaphors to fit the cosmos. Time flows the same everywhere. When we think about time, it seems like something that flows consistently. No matter where you are, seconds tick by, minutes pass, and hours slip away in a predictable rhythm. We often assume that time is the same everywhere. But according to Einstein's theory of relativity, time isn't as uniform as we think. It can stretch and bend, depending on where you are and how fast you're moving. Relativity tells us that time is not an absolute thing that ticks away the same everywhere. Instead, it is relative. It depends on two things: the speed at which you're traveling and the strength of gravity you're in. The stronger the gravity, the slower time moves. The faster you travel, the slower time becomes. This is known as gravitational time dilation and velocity time dilation. In simple terms, if you were near a massive object like a black hole, time would pass more slowly for you than for someone far away from it. This happens because the massive object distorts space-time. Similarly, if you were to travel close to the speed of light, time would slow down for you compared to someone who isn't moving as fast. This was famously illustrated with the twin paradox. One twin stays on Earth, and the other travels in space at high speed. When they reunite, the space-traveling twin is younger than the one who stayed behind. This is not just a theoretical concept. It's been confirmed with experiments. For example, atomic clocks flown around the Earth on high-speed jets tick slightly slower than clocks on the ground, proving that time passes more slowly at higher speeds. The effects may be tiny in our everyday lives, but in extreme conditions, near black holes or at relativistic speeds, the difference is profound. So, while we experience time as a constant in our daily lives, relativity shows us that time is flexible. It bends and stretches based on where we are in the universe and how fast we're moving. Time is not the same everywhere. It's relative to gravity and motion, making the universe's experience of time far more complex than we imagine. The universe doesn't just feel different, it makes time different too. It's a reminder that even the most fundamental things in life are more dynamic and intricate than we often assume. Objects age the same across space. We often assume that time affects all objects in the universe the same way. If you look at an apple on Earth, you might think it ages the same as an apple on a distant planet, or even a star far across the galaxy. Time is a constant, right? It ticks by the same for everyone and everything. But this is another deep misunderstanding about the nature of the universe. Objects don't age the same way across space. In fact, time itself can change depending on the conditions around you. And this means objects age differently depending on where they are and how fast they're moving. One of the most fundamental discoveries of Einstein's theory of relativity is the idea that time isn't universal. It's relative. This means that time flows at different rates depending on two main factors: gravity and velocity. The stronger the gravitational field, the slower time passes. The faster you move, the slower time seems to pass for you compared to someone who is stationary. This has been proven with very precise experiments. For example, clocks on satellites in orbit tick slightly faster than those on the ground because the Earth's gravity is weaker up there. So, what does this mean for objects in space? Imagine two identical clocks, one on Earth and one on a spaceship traveling at a high speed. If you left Earth, traveled around the galaxy, and came back, you would find that the clock on the spaceship has aged less than the one on Earth, even though the two clocks started at the same time. The one on the spaceship, due to its high velocity, would have experienced time moving more slowly. This phenomenon is known as time dilation. Similarly, an object near a massive star or black hole would experience time differently than something far away from such an intense gravitational source. The closer an object is to a strong gravitational field, the slower time passes for it, relative to objects further away. In these extreme environments, the effect becomes much more noticeable. The stronger the gravity, the more pronounced the slowing of time. This idea of time moving differently for different objects might seem strange, but it's real and measurable. The effects are usually tiny for everyday situations, but in the vastness of space, they become significant. In fact, it's not just clocks that are affected. All processes that depend on time, like the aging of atoms, molecules, or even the decay of radioactive elements, are affected by these differences in time flow. This means that two identical objects in different parts of the universe could age at completely different rates. So, time doesn't flow at the same rate for all objects in space. The aging process of anything, whether it's a clock, a person, or a star, is influenced by its velocity and the gravity of nearby objects. The universe is full of different rates of time, and the idea that time is universal is simply a misunderstanding of how reality works. Time travel is completely fictional. The idea of time travel is one of humanity's most intriguing concepts, made famous by books and movies. Who wouldn't want to travel through time, to visit the past or the future? But despite how fun and exciting this idea is, the truth is that time travel, as we imagine it, is not possible. The concept of time travel comes from Albert Einstein's theory of relativity. According to this theory, time is not a constant, it's relative. This means that time moves at different rates depending on how fast you're moving or how strong the gravitational field you're in. This is called time dilation. For example, if you were traveling at close to the speed of light, time would pass slower for you compared to someone who is stationary on Earth. So, in a sense, you could travel forward in time by moving very fast, but it's not as exciting as it sounds. However, time travel to the past doesn't work at all within our current understanding of physics. The grandfather paradox illustrates this perfectly. If you were to travel back in time and prevent your grandfather from meeting your grandmother, you would never be born. So how could you have gone back in time in the first place? This kind of paradox doesn't fit with the laws of physics, and there's no solution to it. Theoretical ideas, like wormholes, have been suggested as possible methods for time travel, but these ideas remain purely speculative. Even if wormholes exist, we have no idea how to use them to travel through time, nor do we know if they could actually be stable enough to use. So, while time travel is a fascinating idea in science fiction, the reality is much less exciting. The only time travel that happens is the natural passage of time, and even then, it's subject to the laws of relativity. We may never be able to hop into a time machine and visit the past or future. Time, as we know it, moves in one direction only forward. The past and future are completely separate. We often think of time as a straight line, a timeline stretching from the past to the future. It feels like the past is a place we can never return to, a fixed part of history that's already written. Meanwhile, the future seems completely unknown, an endless possibility awaiting us. It's easy to imagine that the past and future are completely separate, but this is another misconception about how time works. In reality, the past, present, and future are all connected by the flow of time, While we can't revisit the past or jump ahead to the future, time doesn't split into neat sections like a linear road. Instead, the past and future are part of a continuous fabric that's influenced by the present. One way to think of this is by considering how the past influences the present. Our memories, experiences, and actions are all shaped by things that have already happened, yet they play a crucial role in determining the direction of our lives. On the other hand, the future is not entirely separate from the present either. It's often thought of as a distant unknown, but the choices we make now have a direct impact on what's to come. In physics, this idea is known as causality, the principle that events in the present can affect future events. This doesn't mean we can predict the future with certainty, but it does mean that the future is shaped by the decisions and actions we take in the present. The boundary between the past and the future is not as clear-cut as we might think. They influence each other in ways that we don't always fully understand. Einstein's theory of relativity also plays a role in understanding the connection between past, present, and future. According to relativity, time is not absolute, it's relative. This means that the way we experience time depends on our position in space and the speed at which we're moving. This blurs the lines between past, present, and future, as time itself can stretch and bend depending on our circumstances. The idea that time is rigid and fixed in separate sections is simply not true. Instead, time is fluid, interconnected, and constantly flowing in a way that's influenced by our present actions. So, while we often think of the past and future as separate, fixed parts of time, the truth is that they're much more interconnected. The past influences the present, and the present shapes the future. Time isn't a static line. It's a dynamic force that continuously links all moments together. The past, present, and future are not separate. They are part of a single, flowing experience. All galaxies move away in the same speed. The idea that all galaxies move away from us at the same speed is a common misconception. It's easy to imagine the universe as a giant balloon, with galaxies as the dots on the surface. As the balloon inflates, the dots move farther apart. And it seems logical to assume that they're all moving away from each other at the same rate. After all, the universe is expanding, and it feels like everything is moving away from everything else. But in reality, galaxies don't all move away from us at the same speed. The expansion of the universe is a more complicated process. While it's true that distant galaxies appear to be moving away from us, the speed at which they're receding depends on their distance from us. This relationship is known as Hubble's law. It states that the farther a galaxy is from us, the faster it appears to be moving away. In other words, galaxies that are farther away are moving away from us faster than those that are closer. This doesn't mean that galaxies are traveling through space like cars on a highway. Instead, the fabric of space itself is expanding, and this expansion causes galaxies to move apart. The space between galaxies is stretching, which makes it seem as though the galaxies are moving away from each other. The rate at which they move apart depends on how much space there is between them. This is why galaxies that are further away from us appear to be moving faster. However, this expansion is not uniform everywhere. Some nearby galaxies, like our neighbor, the Andromeda Galaxy, are actually moving toward us. This is due to local gravitational effects that overcome the general expansion of space. So, while most galaxies are receding from us as the universe expands, there are exceptions to the rule, especially on smaller scales. The misconception that all galaxies move away from us at the same speed comes from simplifying the expansion of the universe. While the universe as a whole is expanding, the actual velocities of galaxies vary depending on their distance from us. The farther away a galaxy is, the faster it appears to be moving away. It's a subtle but important distinction that helps us understand the true nature of cosmic expansion. In the grand scale of the universe, everything is moving apart, but the rate at which it happens depends on the distance between the galaxies. As space continues to expand, the universe will keep getting bigger, and galaxies will keep moving farther apart, faster and faster. But that doesn't mean they all move away from us at the same speed. The universe's expansion is far more complex than that. Light loses energy by getting tired. When we think about light, we often imagine it as a perfect, untouchable force that travels through space at a constant speed. Light seems to be invincible. It's the fastest thing we know, and it doesn't seem to lose anything as it travels. But in reality, light does lose energy as it moves through space. The idea that light gets tired is not just a poetic thought. It's a phenomenon called redshift, and it's one of the most important concepts in understanding the universe. Redshift happens because light waves stretch as they travel through expanding space. The further light travels, the more stretched out its wavelength becomes, shifting it toward the red end of the spectrum. This means that the light has lost energy. Its wavelength has become longer, and its frequency has become lower. This effect is similar to the sound of an ambulance siren fading as it moves away. As the ambulance moves farther away, the sound waves stretch out, and the pitch of the siren drops. Light behaves the same way, but instead of a sound wave, it's the electromagnetic wave stretching out over cosmic distances. This stretching of light waves is a direct result of the expansion of the universe. As space expands, the distance between light-emitting objects, like stars and galaxies, also increases. The light that leaves those distant galaxies gets stretched as it travels through this expanding space. The further a galaxy is from us, the more its light is stretched, and the redder it appears. This is why the most distant galaxies appear redder than those closer to us. They're emitting light that has been stretched the most. In a way, light is tired because it's been traveling through an expanding universe for billions of years. The farther it has to travel, the more it loses its energy. But this isn't a sign that light is weakening or dying. It's simply a consequence of the way space itself is growing. The universe is expanding, and this stretching affects all the light that travels through it. Redshift is not just a theoretical concept, it's something we can observe. By studying the redshift of light from distant galaxies, astronomers can measure how fast the universe is expanding. This is how we know that the universe has been expanding since the Big Bang. As light loses energy over time, it gives us a window into the history of the universe itself. It's a cosmic signal that tells us about the expansion of space, the stretching of time, and the gradual tiring of light. So, the next time you think about light, remember, it's not just a perfect, unchanging entity. It's a traveler on a long journey through an expanding universe, gradually losing energy as it moves farther from its source. Light doesn't get tired in the way we imagine. Its energy just shifts, stretched across the vastness of space. The universe is mostly made of stars. When we look up at the night sky, we see countless stars scattered across the heavens. From our perspective on Earth, it's easy to think that the universe is mostly made up of these twinkling points of light. Stars are beautiful, they're bright, and they dominate our view of space. so they must make up most of the universe, right? But the truth is that stars are a relatively small part of the universe's composition. In fact, only a tiny fraction of the universe is made of stars. While stars are indeed essential for creating the elements that make up planets and life, they actually represent a small percentage of the total matter in the cosmos. The vast majority of the universe is made up of dark matter and dark energy. Two mysterious components that we can't see but know exist because of their gravitational effects on visible matter. Dark matter makes up about 27% of the universe, and dark energy accounts for about 68%. These two substances are invisible to us, but their presence is inferred from the way galaxies move and interact with one another. Without dark matter, galaxies wouldn't hold together the way they do. Without dark energy, the universe wouldn't be expanding at the accelerating rate we observe today. Stars, on the other hand, only account for about 5% of the universe. That means everything we see in the night sky, the stars, planets, galaxies, makes up a tiny fraction of the universe's total mass. The rest of the universe is dominated by these invisible forces, which play a critical role in shaping the cosmos. The stars we admire are part of the larger cosmic puzzle, but they are not the majority. Even though stars make up only a small portion of the universe, they are incredibly important. They are the factories where elements are created. Through the process of nuclear fusion, stars produce elements like hydrogen, helium, carbon, and oxygen, the building blocks of life. When stars die, they release these elements into space, enriching the cosmos and creating new stars, planets, and even life. So, while the universe may seem like it's mostly made of stars, the truth is that stars are just one part of the larger cosmic story. They are essential for the formation of matter, but the universe itself is made up of mostly invisible, mysterious forces that we are still working to understand. The stars are only the visible tip of the cosmic iceberg, and the majority of the universe remains hidden from our view. Space and time are separate. For most of human history, space and time were thought to be two separate things. We imagine space as the three-dimensional world around us, the distances between objects, the positions of stars, planets, and galaxies. Time, on the other hand, was seen as a completely different entity. It flowed like a river, marching forward second by second, independent of the physical world. We had no reason to believe that these two concepts, space and time, were related in any meaningful way. But this changed dramatically with Albert Einstein's theory of relativity. Einstein showed us that space and time are not separate at all. Instead, they are part of a unified fabric known as space-time. Space-time is the four-dimensional continuum that combines the three dimensions of space, length, width, and height, with the one dimension of time. In this framework, space and time are interwoven, and one cannot exist without the other. This idea seems strange at first, but it has been confirmed time and time again by experiments and observations. One of the key ideas in relativity is that space and time are flexible. They can stretch and bend depending on the presence of matter and energy. For example, when a massive object, like a star or a planet, is present, it causes the fabric of space-time to warp. This warping is what we experience as gravity. The stronger the gravitational field, the more space-time curves, and the more time slows down in that region. In this sense, gravity is not just a force pulling objects together, but a distortion of the very fabric of space and time itself. This blending of space and time becomes even more apparent when we think about the speed of light. According to relativity, the speed of light is constant. Nothing can move faster than light. This means that no matter how fast you are moving, light always travels at the same speed relative to you. But this also means that space and time are relative. The faster you move, the more time slows down for you compared to someone who is stationary. This is why astronauts aboard fast-moving spacecraft age more slowly than people on Earth. In a way, space and time are two sides of the same coin. They are inseparable, and together they form the fabric of the universe. If one changes, the other is affected as well. Time is not an independent, separate dimension, but rather an essential part of the universe's structure. The boundaries between space and time blur, and we begin to understand that they are both integral to our understanding of the cosmos. So, the next time you think about space and time, remember that they are not separate entities. They are two aspects of the same reality, space-time. And in this unified framework, the laws of physics become clearer and more interconnected. Space and time are not just distant, abstract concepts. They are living, breathing elements of the universe that shape the very way we experience reality. Dark matter is just invisible, regular matter. Dark matter is one of the biggest mysteries of modern physics. We can't see it, we can't touch it, and we can't directly detect it. Yet, we know it exists because of the way it influences visible matter through gravity. It was first proposed to explain why galaxies rotate the way they do, too fast to stay intact with the amount of visible matter they contain. Without the gravitational pull of dark matter, these galaxies should fly apart, but instead, they stay bound together, suggesting there's more mass present than what we can see. For many years, scientists assumed that dark matter was just ordinary, invisible matter, atoms and particles that don't interact with light or other forms of electromagnetic radiation. This idea makes sense at first. If dark matter is just matter we can't see, maybe it's made of the same types of particles as the matter we know, but it doesn't emit, absorb, or reflect light. It doesn't interact with electromagnetic forces, which is why it's invisible. But while this explanation was convenient, it turns out to be a bit too simple. The truth is that dark matter is not the same as the regular matter that makes up stars, planets, and us. It's not made of atoms and molecules in the way that normal matter is. Instead, dark matter is thought to be composed of particles that don't interact with electromagnetic forces, but it still interacts with gravity. These particles are likely weakly interacting massive particles, WIMPs, but we've never been able to detect them directly. We can only observe their effects on the motion of galaxies and other large-scale structures in the universe. One of the key differences between dark matter and regular matter is how they interact with light. Regular matter can absorb, emit, and reflect light, which is why we can see it. Dark matter, on the other hand, doesn't interact with light in any way. This is why it's dark and invisible. But despite not interacting with light, dark matter has a significant effect on the structure of the universe. It makes up about 27% of the universe's total mass energy content, while visible matter, the stuff we can see, only makes up about 5%. This realization changes the way we think about dark matter. It's not just invisible regular matter, as we once thought. It's a different kind of matter altogether, made of particles that don't behave the same way as the matter we're familiar with. It interacts through gravity, but not through the electromagnetic forces that govern normal matter. It's this unique property that makes dark matter so elusive and difficult to study. but it's also what makes it so crucial to understanding the universe. Without dark matter, the structure of the universe would be completely different. Galaxies wouldn't form the way they do, and the large-scale structure of the cosmos would be fundamentally altered. So, while dark matter might seem like a simple concept, just invisible regular matter, it's actually far more complex. It's not the same as the matter we're familiar with, and it's this difference that makes dark matter one of the greatest unsolved mysteries in physics. The universe is infinite in both time and space. The idea of infinity is mind-boggling. When we think of the universe, it's natural to imagine it as an infinite expanse, an endless sea of stars, galaxies, and cosmic structures stretching out forever in every direction. But does the universe really go on infinitely, or is it limited in both time and space? For centuries, humans have debated whether the universe is truly infinite or if it has boundaries. The idea of infinity is so large, so abstract, that it's hard for us to comprehend. The concept of something having no end is difficult to grasp. Yet, current scientific models suggest that the universe may indeed be infinite, at least in terms of its spatial extent. Space, as we know it, is expanding. Galaxies are moving away from each other, and the space between them is stretching. The universe is not just growing, but it's also growing at an accelerating rate. This phenomenon is driven by something mysterious called dark energy, which makes up a significant portion of the universe's energy content. While the universe is expanding, it's important to note that space itself is what is expanding, not the galaxies moving through space. This means that as space stretches, the distances between galaxies increase. But if space itself is infinite, what about time? Time is usually thought of as having a clear starting point, the Big Bang. If the universe had a beginning, does that mean it has an end too? While we don't know exactly how the universe will end, current models suggest that it could keep expanding forever. There's no reason to think the expansion will stop. In fact, the acceleration of the expansion suggests that the universe will continue to stretch indefinitely. If this is true, it would mean that both time and space are infinite. The universe would have no end in sight, no limit to its size, no point where it will stop growing. The notion of an infinite universe doesn't just apply to space, but also to time. If the universe will continue to expand forever, time itself will continue moving forward. But this doesn't mean time is eternal, in the sense that everything will remain the same. As space stretches, the energy in the universe will eventually dissipate, and stars will burn out, leading to what scientists call the heat death of the universe. In this scenario, the universe will continue expanding, but it will be a cold, empty place, with little energy left to sustain life or motion. While this might seem like the end of everything, it's also the continuation of the universe in an infinite timeline. So, while the universe may seem vast and finite from our perspective, it's possible that it's both spatially and temporally infinite. It's hard to comprehend an infinite universe, but current science suggests that it's a real possibility. Whether the universe expands forever or eventually reaches a limit, we know that it has existed for billions of years and will likely continue for billions more. Infinity is a concept that challenges our understanding of existence, but the universe might just be infinite after all. The universe is static now. For a long time, humans believed that the universe was a static place, a fixed, unchanging entity. This idea made sense at the time, especially since the stars and galaxies we observed seemed to remain in the same relative positions for generations. the concept of a static universe, one that doesn't change or evolve over time, was a comforting one. After all, if the universe is unchanging, then it's easier to understand and accept. But this idea was shattered in the early 20th century when astronomers like Edwin Hubble discovered that the universe is actually expanding. The discovery that the universe is expanding was a turning point in our understanding of the cosmos. It was based on observations of distant galaxies, which appeared to be moving away from us. The farther the galaxy, the faster it was receding. This observation was the first evidence that the universe is not static, but dynamic. It's constantly growing and evolving. The expansion of the universe means that space itself is stretching. And as space stretches, the distances between galaxies increase. This discovery fundamentally changed our understanding of the universe and its history. But the idea that the universe is expanding doesn't just mean that it was once smaller. It also means that the universe is far from static now. The expansion of space is ongoing, and it's accelerating. This discovery, combined with the detection of dark energy, has led scientists to conclude that the universe will continue to expand forever. There's no reason to believe that the expansion will stop anytime soon. In fact, the expansion is happening at an increasingly rapid rate. The notion that the universe is static also ignores the incredible dynamism within galaxies themselves. Stars are born, live, and die. Galaxies collide and merge. Planets form and evolve. Even though the universe is expanding, it's far from unchanging. It's filled with constant motion and transformation. New stars are born from the gas and dust of old ones, and black holes continue to form and grow. Supernovae explode in violent bursts of energy, and galaxies continue to evolve as they interact with each other. In fact, the universe's expansion itself is evidence of its dynamic nature. As space stretches, it creates new possibilities for the formation of matter and energy. The universe is not static. It's constantly changing, growing, and evolving. The idea of a static universe was once comforting, but it's also limiting. The truth is far more exciting. The universe is a living, breathing entity, full of energy and motion, and it's far from static. It's a reminder that the universe is always in flux, always moving, and always evolving. So, the next time you think of the universe as a fixed, unchanging place, remember that it's anything but. It's constantly expanding, constantly changing, and constantly evolving. The universe isn't static. It's alive with motion, energy, and possibility. The only constant is change itself. The speed of light is always experienced the same. We often hear that nothing can travel faster than the speed of light, and that speed, 299,792 kilometers per second, is the ultimate speed limit of the universe. This idea is deeply ingrained in our minds, and it seems like a constant, undeniable fact. The speed of light is fixed, right? It's the same for everyone, no matter where they are or how fast they're moving. However, this assumption is not entirely correct. The truth is more nuanced, and it all boils down to the concept of relative motion in the universe. In Einstein's theory of relativity, one of the most surprising conclusions is that the speed of light is indeed the same for everyone. But it's not the same in the way you might expect. What Einstein discovered was that light always travels at the same speed, regardless of how fast the observer is moving. Whether you're sitting still, running at high speed, or traveling close to the speed of light yourself, light will always move at the same speed relative to you. This might sound counterintuitive. In our everyday experience, if we're moving towards something, it seems like we should get there faster. For example, if you're running toward a car that's driving toward you, the relative speed at which you approach the car is the sum of your speeds. But with light, things are different. If you shine a flashlight in the direction you're moving, the speed of light will still be the same, whether you're stationary, moving, or even traveling near light speed. This phenomenon is known as the invariance of the speed of light. It's a cornerstone of relativity, and it has profound implications for how we experience the universe. It means that no matter how fast you're moving, you can never catch up to light. If you travel at 99% of the speed of light, light will still pass you by at the same speed. It's not that light is slower in certain situations. It's that the laws of physics are designed to make sure the speed of light remains constant for everyone. This doesn't mean that the speed of light is a universal constant in every sense. Instead, it means that it's always measured the same, no matter your motion or perspective. Light speed can appear different when observed from different reference frames, but it's always measured the same when calculated relative to the speed of the observer. This is part of the reason why time dilation and length contraction occur in relativity. As an object moves faster, time appears to slow down, and length contracts. In the grand scheme of the universe, this invariance of light speed helps maintain the fundamental structure of reality. It ensures that the laws of physics are the same for everyone, everywhere, regardless of motion. So, while we may think of the speed of light as something we experience in a very fixed way, the truth is that light's speed is woven into the very fabric of space-time itself. A light year is a measure of time. When we hear the term light year, it's easy to assume it refers to time. After all, it has the word year in it, so it sounds like a measure of how long light takes to travel from one point to another. But this is a misunderstanding. A light year is not a measure of time at all. It's actually a measure of distance. The concept of a light year is used to describe how far light travels in 1 year. Since light travels incredibly fast, 299,792 kilometers per second. Over the course of a year, it can cover an enormous distance. Specifically, 1 light year is approximately 9.36 trillion kilometers. This is how we measure the vast distances between stars and galaxies, as they're so far apart that we need a much larger unit of measurement than kilometers or miles. A light year is useful because it allows astronomers to describe these enormous distances in a way that's easy to understand. Instead of saying, the star Alpha Centauri is about 40.2 trillion kilometers away, it's much simpler to say, it's 4.2 light years away. This helps put the vast scale of the universe into perspective. Even the nearest stars are millions of times farther away than we can easily comprehend with traditional units of distance. The confusion often arises because we associate the word year with time. And indeed, it takes light a specific amount of time to travel 1 light year. But that time is extremely short, just under 8.3 minutes for light to travel from the sun to Earth. When we say something is a certain number of light years away, we're talking about the distance light would travel in that amount of time, not how long it would take to get there. In a way, using light years is a reminder that time and distance are interconnected. In the vastness of space, the travel time for light is more important than the concept of a year as we know it. It shows us just how far light can travel and how much space exists between the objects we see in the night sky. It's a unit designed to help us grasp the incomprehensible scale of the universe, not just to measure time. So, While a light year may sound like a unit of time, it's actually a unit of distance. It helps us understand the enormous distances between stars, planets, and galaxies. And as we look deeper into the cosmos, we realize that a light year is more than just a measurement. It's a tool that connects the concept of time and distance, giving us a new way to explore the vastness of space. Light always travels in straight lines. When we think about light, we often imagine it traveling in a straight line, like an arrow fired from a bow. It's easy to assume that light always moves in straight paths, because that's how we experience it in our everyday lives. We see a beam of light shining across a room, and it appears to travel in a straight line from the source to the object it illuminates. But this idea that light always travels in straight lines is a misunderstanding of how light behaves in certain circumstances. While light does generally travel in straight lines in most situations, there are times when it doesn't. In fact, light is influenced by various factors that can cause it to bend, curve, or scatter in ways we might not expect. The most well-known example of this is gravitational lensing. According to Einstein's theory of relativity, massive objects like stars and galaxies can bend the fabric of space-time, causing light to follow a curved path instead of a straight one. This phenomenon is known as gravitational lensing, and it allows us to observe distant galaxies and stars that would otherwise be hidden from view. Gravitational lensing occurs because the gravity of a massive object distorts the space around it, causing light to bend as it passes through. It's similar to the way light bends when it passes through a prism, splitting into a spectrum of colors. In this case, however, the bending of light is caused by gravity, not a change in the medium through which the light is traveling. This effect has been observed numerous times, allowing scientists to study distant objects in the universe that are otherwise too far away to see. But light doesn't only bend due to gravity, it can also be refracted, or bent, when it passes through different media. For example, when light passes from air into water, it slows down and changes direction. This is why a straw looks bent when placed in a glass of water. The light traveling from the straw to your eyes is refracted as it moves from the water to the air. This phenomenon is called refraction, and it's the principle behind the functioning of lenses, such as those in eyeglasses and telescopes. Another example of light not traveling in a straight line is scattering. When light encounters small particles in the atmosphere, such as dust or water droplets, it can scatter in different directions. This is why the sky appears blue during the day, the shorter wavelengths of light. Blue and violet are scattered more than the longer wavelengths, red and yellow. This scattering of light also explains why the sun looks red or orange during sunrise and sunset, as the light has to pass through more of Earth's atmosphere, scattering the shorter wavelengths and leaving the longer wavelengths to reach our eyes. So, while light does often travel in straight lines, there are several instances where it doesn't. The behavior of light is influenced by the medium it's traveling through and the forces acting upon it, whether it's the bending of light due to gravity, the refraction of light through different materials, or the scattering of light by particles in the atmosphere. Light's path is not always a straight line. This makes light a more complex and dynamic phenomenon than we might first think. You see stars as they are right now. When you look up at the night sky, you might think you're seeing stars just as they are right now, twinkling in the present moment. After all, the light from those stars is traveling through space, and it reaches your eyes at the very moment you gaze upon them. Right. Well, this is a common misunderstanding. The truth is that when you look at stars, you're actually seeing them as they were in the past. The farther away the star, the older the light you're seeing. This is because light takes time to travel across vast distances, and the universe is so incredibly large that even light, traveling at the speed of 299,792 kilometers per second, takes a significant amount of time to reach us from distant stars. The light you see from a star that's a few light years away is light that left that star years ago. If a star is 10 light years away, the light you see tonight left that star 10 years ago. This means you're essentially looking at the past. The farther the star, the further back in time you're looking. Stars that are millions or even billions of light years away are showing you light that left them long before humans ever walked the Earth. For example, if you observe a galaxy that's 2 million light years away, you're looking at light that left that galaxy 2 million years ago. You're seeing the galaxy as it was in the distant past, not as it is today. It's a fascinating concept because it means that every time you look up at the night sky, you're looking at a snapshot of the universe's history. This phenomenon, known as look-back time, is one of the reasons why studying distant stars and galaxies is so important for astronomers. By looking at distant objects, we're able to look back in time and learn more about the universe's early stages. It's like having a cosmic time machine, but the farther we look, the further back in time we go. This also means that when we observe the universe, we're not seeing it as it is in real time, but as it was when the light first began its journey toward us. In a way, the stars are always in the past, constantly sending out light that travels across the vast stretches of space. Even the stars we see in the night sky might no longer exist in the same form. A star might have exploded in a supernova or collapsed into a black hole, but the light from those events could still be traveling through space, reaching us long after the actual event occurred. So, the next time you look up at the stars, remember, you're not seeing them as they are right now. You're seeing them as they were when their light began its journey to Earth. Time is absolute. We tend to think of time as something fixed, something that flows in the same way for everyone, everywhere. It's the same for all of us, no matter where we are or what we're doing. Time is often seen as a constant, something that ticks away uniformly in a straight line, but this is a misconception. The truth is that time is not absolute. In fact, time behaves differently depending on where you are and how fast you're moving. This idea comes from Einstein's theory of relativity, which showed us that time is not the same for everyone. Time, in fact, is relative. It depends on your frame of reference. The faster you move, the slower time passes for you, relative to someone who is stationary. This phenomenon, known as time dilation, is not just a theoretical idea. It's been experimentally confirmed in many ways. For example, atomic clocks placed on fast-moving jets have shown that time actually passes slower for them compared to clocks on the ground. This means that time isn't a constant, universal force. The ticking of the clock depends on how fast you're moving and how strong the gravitational field you're in is. The closer you are to a massive object, like a planet or a star, the slower time moves for you, and the faster you travel, the more time slows down for you compared to someone who is stationary. The classic example of this is the twin paradox. Imagine two identical twins. One stays on Earth, while the other travels through space at close to the speed of light. When the traveling twin returns, they will be younger than the twin who stayed on Earth. This is because time passed more slowly for the traveling twin due to their high speed. This isn't a trick or an illusion. It's a real, physical effect predicted by relativity and confirmed by experiments. But time dilation doesn't only happen with high speeds. It also occurs near strong gravitational fields. The stronger the gravity, the slower time moves. This is why time moves slightly faster for people at the top of a tall building compared to those at the bottom. Gravity has a very subtle effect on time, but it's real and measurable. So, time is not absolute. It's not a constant. Ticking away in the same way for everyone, it's fluid, bending and stretching depending on your speed and the strength of gravity around you. The more we understand time, the more we realize just how complex it is. Time is not something we can hold on to or control. It's an ever-changing, ever-flowing force that adapts to the very fabric of space and time. The idea of absolute time is just another misconception, one that limits our understanding of the universe. Time is relative. It's a part of the universe's structure, and like everything else in the cosmos, it behaves according to the laws of physics. Objects age the same across space. It's easy to assume that objects in the universe age at the same rate. After all, time moves forward at the same pace for everyone, doesn't it? If you look at a star in the night sky, you might think it's aging at the same rate as everything else in the universe. However, this is a misunderstanding. The truth is, objects in space age at different rates depending on where they are, how fast they're moving, and how much gravity they're experiencing. One of the key principles of Einstein's theory of relativity is that time is not the same for everyone, everywhere. This means that time can pass at different rates depending on the conditions of the environment. This phenomenon is known as time dilation. The stronger the gravitational field, the slower time moves. This effect is not just theoretical. It's been experimentally confirmed by scientists using atomic clocks. For example, clocks on satellites moving in Earth's orbit tick slightly faster than those on the surface of the Earth, due to the difference in gravitational pull. Similarly, the faster you move, the slower time passes for you, compared to someone who is stationary. This effect becomes more noticeable as you approach the speed of light. If you were traveling at nearly the speed of light, time would pass much more slowly for you compared to someone on Earth. This means that if you were to travel through space at near light speed and then return to Earth, you would have aged less than the people who stayed behind. Your body would have experienced time much more slowly. This is a big deal when you consider the vastness of space. It means that objects in different parts of the universe, or even in the same part but moving at different speeds, are aging at different rates. The stars you see in the night sky might seem like they've been burning for billions of years, but in reality, they're not all aging the same way. The ones in distant galaxies may be younger in terms of the time that has passed for them, depending on how fast they're moving or how close they are to massive objects. The concept of time dilation also has important implications for how we understand the universe's past and future. Since time flows differently depending on the conditions, we can't always assume that time has passed the same way for all objects in the universe. The stars and galaxies we observe may have experienced different amounts of time compared to us, even though we perceive them as being from the same era of the universe. It's a reminder that time is more fluid than we think, and it's not always the same for everything. So, the next time you look at a star or think about the vastness of space, remember that objects don't age the same way across space. Time is relative. It depends on the conditions of the universe around you, gravity, speed, and other factors. The stars might look the same from a distance, but in reality, they're experiencing time in their own unique ways, and that's one of the many ways the universe surprises us. Time travel is completely fictional. The The concept of time travel has fascinated people for centuries. Whether it's the idea of visiting the past to change events or seeing the future to predict what's coming, time travel captures the imagination in books, movies, and dreams. It seems so simple. Travel through time like you would travel through space. Just jump to another point in time. But the truth is, time travel as we think of it is not possible. This may be disappointing for those who dream of jumping back to witness historical events or into the future to see what's to come. But the reality is that time, in the way we think about it, doesn't work like that. While Einstein's theory of relativity has shown us that time is relative, that it can be affected by speed and gravity, it also shows us that time travel to the past isn't possible in the way we imagine. The grandfather paradox, one of the most famous thought experiments in physics, highlights the contradiction in time travel. If you were to go back and change something in the past, it could prevent you from ever existing in the first place. This creates a paradox where actions in the past could eliminate the cause that allowed time travel to happen. Even though time dilation allows for a form of time travel where time slows down the faster you travel, such as with astronauts traveling near the speed of light, this is not the kind of time travel where you can revisit past events. Instead, time travel in this context would simply make you age slower relative to those around you. You wouldn't be able to go back to any specific point in the past or jump ahead to a future event. You would only experience time differently due to your speed, and only for a brief period before returning to a common reference frame. On top of that, there are theoretical ideas like wormholes, tunnels in space-time that could, in theory, allow for time travel. However, these ideas are purely theoretical and have never been observed. The conditions required to create a stable wormhole would require massive amounts of energy and exotic matter that we don't have access to. Even if they did exist, we would need to find a way to use them safely, which remains far beyond our current scientific understanding. So, while time travel is a fascinating concept in fiction, the truth is that it doesn't work the way we imagine. Time is not a river that you can jump in and out of, and the universe doesn't have a mechanism to allow for the kind of time travel we see in movies. The past is locked, and the future is uncertain. Time marches forward, and we move with it, one moment at a time. The dream of changing history or peering into the future might remain just that, dreams. But even without time travel, there's still so much wonder to explore in the present and the future. Faster than light travel breaks causality. The idea of traveling faster than light has always been a dream for science fiction fans. It's the stuff of intergalactic adventures and starships zipping through the cosmos. If we could travel faster than light, we could reach distant stars in an instant, explore new worlds, and even visit distant galaxies. However, there's a major issue with faster than light: FTL, travel that makes it impossible in the way we envision it. It breaks causality. Causality is the principle that cause comes before effect. In simpler terms, it's the idea that events happen in a specific order. If I throw a ball, it moves through the air before hitting the ground. That's cause and effect. But if we could travel faster than light, we could reverse the order of events, creating paradoxes that would make the concept of cause and effect meaningless. In a universe where FTL travel is possible, events could be observed happening in reverse order, violating the natural flow of time. This is the problem with FTL travel. It allows for the possibility of events happening before their cause. For example, imagine you could travel faster than light to a point in the future and somehow interact with something that had already happened. This would create a situation where the effect of an event, Your actions in the future occurs before the cause, the event that led to those actions. This would create logical contradictions, making it impossible to maintain a consistent, coherent timeline. The famous grandfather paradox is one example of this. If you could travel faster than light, you could potentially go back in time and change something significant, like preventing your grandfather from meeting your grandmother. If you did that, you would never be born, which would prevent you from traveling back in time in the first place. This paradox doesn't just exist in the realm of imagination. It's a fundamental problem with the laws of physics if FTL travel were possible. In addition to paradoxes, FTL travel would also violate one of the key principles of relativity, the idea that the speed of light is a universal limit. According to Einstein's theory of relativity, the speed of light is the maximum speed at which information can travel. If something were to exceed this limit, it would result in violations of causality. In other words, faster than light travel would mean that information could be sent back in time, creating contradictions and making the concept of time itself unreliable. While faster than light travel remains a popular concept in science fiction, the laws of physics suggest that it's not possible without causing serious issues. The constraints of causality are deeply woven into the fabric of our universe, and violating them would unravel the very structure of reality. So, as much as we'd love to travel to distant stars at FTL speeds, it seems that for now, and perhaps forever, the speed of light remains the ultimate speed limit. The future is already fixed. The idea that the future is already fixed is something that many people have pondered for centuries. We often think of time as a road that stretches ahead of us, full of potential and possibility. But what if the future is already set in stone? What if everything that happens, every choice, every event, is already determined? This idea, known as determinism, suggests that every moment in time, from the past to the future, is inevitable and fixed based on the laws of physics. Determinism implies that every event in the universe is the result of preceding events and conditions. This includes everything from the motion of galaxies to the decisions we make in our daily lives. According to this perspective, if we knew the current state of the universe, we could predict everything that will happen in the future. It's as if the future is already written, waiting for us to catch up to it. One way to think about this is by considering the laws of physics. The universe operates under a set of rules that govern how everything works. From the movement of planets to the behavior of particles, everything follows these rules. If we knew all the variables, where every particle is, how fast it's moving, and what forces are acting upon it, we could theoretically predict every future event. The universe would be like a giant clock, ticking away according to its internal mechanics. In this view, the future isn't something that can be shaped by our choices. It's simply a consequence of everything that has come before. However, this deterministic view of the universe is not universally accepted. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, introduces an element of uncertainty. At the quantum level, particles don't have definite positions or speeds until they are measured. This randomness at the fundamental level of reality challenges the idea that the future is completely fixed. If the smallest particles are unpredictable, then maybe the future is not as determined as we think. Even so, some argue that determinism and quantum mechanics can coexist. One possibility is that while the behavior of individual particles may be random, the overall structure of the universe could still follow predictable patterns. In this view, the future might be fixed in a probabilistic sense, meaning that while we can't predict every tiny detail, The big events and trends in the universe are still governed by deterministic laws. Ultimately, the question of whether the future is already fixed remains an open one. The truth may be somewhere in between, with some aspects of the future determined and others still up in the air. But whether or not the future is truly fixed, it's clear that our perception of time and causality is much more complex than we might have originally thought. The universe is a dynamic, interconnected system, and even if the future is influenced by the past, it remains full of mysteries waiting to be uncovered. There is a universal now moment. The idea that there is a universal now is something that most people take for granted. We all experience time in a similar way. Moments pass by one after another, and we feel like we're all living in the same present. The clock ticks for everyone, everywhere, at the same pace, and this gives us the illusion that we're all experiencing the same now. But in reality, there's no universal now. Einstein's theory of relativity shattered this common assumption. According to relativity, time is relative. It depends on your position and speed. This means that what one person experiences as the present may not be the same as someone else's present. Time is not the same for everyone, everywhere. In fact, there's no universal moment in time that everyone experiences at the same instant. Instead, the concept of now is different for each observer, and it changes depending on how fast you're moving and where you are in the universe. This idea can be difficult to grasp because we're so accustomed to thinking of time as a linear progression, a single, universal timeline that everyone shares. But according to relativity, two people moving at different speeds or experiencing different gravitational fields will not agree on the exact moment in time. For example, if you're traveling near the speed of light and someone else is standing still, you will experience time differently. The person standing still will see you moving through time more slowly than they are. This means that each of you will have a different perception of the now. The idea of a universal now is also complicated by the fact that light takes time to travel. When we look at distant stars or galaxies, we're seeing them as they were in the past. The farther away an object is, the older the light we see from it. So, the light from the stars we observe today left those stars millions or even billions of years ago. In a sense, when we look at the night sky, we're looking at the past, not the present. This doesn't just apply to distant objects in space. It also affects our daily lives. For instance, when we make a phone call to someone across the globe, we're not talking in real time. There's a slight delay as the signal travels through the cables and satellites. The same happens with the light from the sun. It takes approximately 8 minutes for sunlight to reach us. So, in a very real sense, we're not experiencing the now of the sun, but a slightly delayed version of it. So, the idea of a universal now doesn't hold up when we consider the effects of relativity and the speed of light. There's no single, universal present moment that everyone shares. Instead, time is experienced differently depending on where you are and how fast you're moving. This means that the now you experience is unique to you, and it's shaped by the movement and gravity of your particular situation. Time, it turns out, is far more fluid and subjective than we might have imagined. There is no universal now moment, only a collection of individual moments, each shaped by the observer's frame of reference. The universe doesn't operate on a single, universal clock. Instead, it's a vast and complex system where time is experienced in many different ways by different observers. Nothing moves faster than light, including space itself. When we think about the speed of light, it seems like a hard and fast rule. The speed of light is 299,792 kilometers per second, and nothing can exceed it, right? It's a universal speed limit, a cornerstone of modern physics. But here's the twist. Nothing moves faster than light, including space itself. This idea might seem counterintuitive at first, especially when we talk about the expansion of the universe. After all, we know that galaxies are moving away from each other at incredible speeds. But the key is that space itself isn't bound by the same rules as objects within space. In the expanding universe, galaxies appear to be moving away from us, and the farther away a galaxy is, the faster it seems to be moving. This is called cosmic expansion. It's the stretching of space itself, not the galaxies moving through space like a car on a highway. As space expands, it causes galaxies to move apart, and because space itself can expand at a faster rate than the speed of light, galaxies can recede from each other at speeds greater than the speed of light. This might sound like a paradox. How can something move faster than light if nothing can exceed that speed? The answer lies in the fact that it's not the galaxies themselves moving faster than light, but the fabric of space itself stretching. In this case, the galaxies are not moving in the traditional sense. They are simply carried along with the expanding space. Space itself is not bound by the speed limit of light, and that's what allows it to expand at faster than light speeds. This expansion is not limited by the same constraints that apply to objects traveling through space. It's important to note that this doesn't violate the laws of relativity. The speed of light as a limit applies to objects moving through space, not to the expansion of space itself. The speed of light is still the ultimate speed limit for anything that is actually moving through space. But space can stretch and expand in a way that allows galaxies to move away from each other faster than light without breaking any physical laws. This phenomenon has been observed in the universe's history. For example, during the inflationary period of the early universe, space expanded at a rate much faster than the speed of light. This expansion was responsible for the rapid growth of the universe during the first moments after the Big Bang. Even today, the universe is still expanding, and distant galaxies are receding from us at faster than light speeds due to the stretching of space. So, while it might seem like a violation of the laws of physics, the expansion of space is entirely consistent with the theory of relativity. Nothing in the universe can move faster than the speed of light through space, but space itself can expand faster than light, carrying galaxies along with it. It's a subtle distinction, but an important one that helps explain the accelerating expansion of the universe. Space travel is just about going faster. When we think about space travel, the first thing that comes to mind is usually speed. It makes sense, right? To travel to the stars, we just need to go fast enough, and eventually, we'll reach distant planets and galaxies. We have rockets and spacecraft, so all we need is better propulsion, more fuel, and we're good to go. But the reality of space travel is much more complex than simply going faster. Speed alone is not enough to make space travel a viable option for interstellar journeys. First, let's talk about the vast distances involved. The closest star to Earth, Proxima Centauri, is about 4.24 light years away. That means light takes 4.24 years to travel from Earth to Proxima Centauri. Even if we could build a spacecraft capable of traveling at 1% of the speed of light, which is far beyond our current technological capabilities, it would still take over 400 years to reach this nearby star. That's a long time, and we're not even talking about the billions of stars in the galaxy that are much farther away. The vastness of space means that speed alone won't solve the problem of how to travel to distant stars. We'd need spacecraft capable of traveling far faster than anything we've ever built, even with the fastest spacecraft we currently have, like NASA's Parker Solar Probe, which travels at about 700,000 kilometers per hour. It would still take over 6,000 years to reach Proxima Centauri. This is where the limits of speed become apparent. Going faster isn't the only solution. We need a different approach. Another challenge with space travel is energy. The faster you go, the more energy you need to achieve speeds even approaching a significant fraction of the speed of light. We would need massive amounts of energy, more than we can currently generate or store. The energy required to accelerate a spacecraft to a significant percentage of the speed of light increases exponentially as you approach light speed. This is because, according to Einstein's theory of relativity, an object's mass increases as it approaches the speed of light, making it even harder to accelerate. Additionally, space travel involves more than just getting from point A to point B. There are other critical factors to consider, like life support systems, radiation protection, and the effects of long-term space travel on the human body. The vacuum of space is filled with radiation from the sun and cosmic rays that can be harmful to astronauts. The absence of gravity for long periods can cause muscle atrophy, bone density loss, and other health problems. These issues must be addressed before we can think about sending humans on long-duration space missions. So, while speed is certainly important in space travel, it's only part of the equation. The challenges of distance, energy, and the effects of space on human health mean that we need much more than faster propulsion systems to make interstellar travel a reality. We must also consider new propulsion technologies, such as nuclear fusion, antimatter, or even theoretical concepts like warp drives or wormholes. Space travel isn't just about going faster. It's about developing entirely new technologies and methods to tackle the challenges of vast distances, limited energy, and human survival in space. While we may one day travel to other stars, the journey will require much more than just a faster spacecraft. It will require innovations that we are just beginning to imagine. The past and future are completely separate. We tend to think of the past and future as two separate, distinct realms of time. The past is something that's already happened, fixed in history, and unchangeable. The future, on the other hand, is something that's yet to come, full of possibility and uncertainty. It feels like these two parts of time are completely separate, like two bookends on either side of the present. But this view of time as a strict separation between past and future is a misunderstanding of how time really works. In the universe, time doesn't neatly divide itself into the past and the future. Instead, time is a continuous flow, with each moment leading naturally into the next. The past influences the present, and the present shapes the future, creating an ongoing, interconnected chain of events. The idea that the past and future are completely separate is a concept we impose on time because it makes sense to us. But in reality, time is not as rigid and separate as it seems. One way to understand this is by considering the concept of causality. In a universe governed by causality, the future is influenced by the present, and the present is influenced by the past. The flow of time is not unidirectional, and events are not completely isolated from each other. Each moment builds on the previous one, creating a web of connections that bind the past, present, and future together. The actions we take now can have far-reaching consequences for the future, and the events of the past have shaped the world we live in today. Even in physics, time doesn't adhere strictly to a past-future separation. The laws of physics, including those that govern motion, gravity, and energy, apply equally to the past and the future. The equations that describe the universe work in both directions of time, meaning that the same physical laws govern the past and future events. In theory, if you could reverse the flow of time, the processes in the universe would work the same way. This idea is known as time symmetry, and it shows that the future and the past are not as separate as we usually think. Instead, they are both part of the same continuous fabric of time. In addition, our perception of time itself is based on how we experience the present moment. We experience time as flowing in one direction, from the past through the present and into the future. But our perception of time doesn't fully capture the true nature of time itself. In reality, time might be just another dimension, like space, where past, present, and future are not strictly separated. Time may be a continuous loop, where events and moments are interconnected, and the boundaries between past and future are not as sharp as we imagine. The idea that the past and future are completely separate is rooted in our perception of time, but it doesn't fully reflect the way time works in the universe. Time is a flowing, interconnected fabric where the past, present, and future are part of a continuous whole. The events of the past shape the present, and the present influences the future. Instead of seeing time as a rigid division between the past and future, we should see it as a dynamic and interconnected process, where all moments are part of the same ongoing story. All galaxies move away at the same speed. When we observe the night sky, it's easy to think that all galaxies are moving away from us at the same rate. After all, the universe is expanding, and galaxies are constantly receding from each other, right? If the universe is expanding uniformly, it makes sense to assume that all galaxies are moving away from us at the same speed. But this is actually a misunderstanding of how cosmic expansion works. The truth is that galaxies don't all move away from us at the same speed. Instead, the speed at which a galaxy appears to be receding from us depends on its distance from Earth. This relationship is described by Hubble's law, which states that the farther a galaxy is from us, the faster it appears to be moving away. In other words, galaxies that are farther away from us are moving away faster than those that are closer. This effect is due to the expansion of space itself, not because galaxies are physically moving through space like cars driving down a road. As space expands, the distance between galaxies increases, and this expansion causes galaxies to move away from each other. The farther apart two galaxies are, the more space there is between them, and the faster they appear to be receding. This is why distant galaxies seem to be moving away from us at much higher speeds compared to nearby ones. One of the key points to understand here is that this recession of galaxies isn't a result of them traveling through space at high speeds, but rather the stretching of space itself. Space is expanding, and as it does, it carries galaxies with it. This means that the faster galaxies are moving away from each other isn't because they are individually traveling faster, but because the fabric of space itself is stretching and carrying the galaxies along with it. This expansion is also uniform in all directions, meaning that every galaxy, no matter where it is in the universe, will observe every other galaxy moving away from it. However, this doesn't mean that all galaxies are moving away from us at the same speed. The speed at which a galaxy is receding depends on how far it is from us. This means that when we look at distant galaxies, They appear to be moving faster than those closer to us, but they're not all moving at the same speed. It's important to note that while this concept applies on cosmic scales, it doesn't work the same way on smaller scales. On the scale of our local group of galaxies, such as the Milky Way and the Andromeda Galaxy, gravity dominates over the expansion of space. These galaxies are actually moving toward each other, not away. In fact, the Andromeda Galaxy is on a collision course with the Milky Way, and the two galaxies are expected to merge in about 4.5 billion years. So, while it's true that galaxies are receding from us as the universe expands, they don't all move away at the same speed. The farther away a galaxy is, the faster it appears to be moving, due to the stretching of space itself. The universe's expansion is more complex than just everything moving apart at a uniform rate. Instead, it's a dynamic process that depends on the distance between galaxies and the expansion of space over time. Light loses energy by getting tired. When we think of light, we often imagine it as something perfect, unchanging, and infinitely fast. Light travels through space at an incredible speed, and we assume it keeps that same speed and energy as it moves through the cosmos. However, light does not always maintain the same energy level as it travels, especially over vast distances. The concept that light gets tired might seem strange, but it actually has a basis in the physics of the universe. As light travels through the expanding universe, it loses energy. This phenomenon is known as redshift. Redshift occurs when the wavelength of light stretches, causing it to shift toward the red end of the spectrum. The farther light travels, the more its wavelength gets stretched, which results in a loss of energy. This stretching happens because space itself is expanding, and as the universe grows, it causes the distance between light-emitting objects, like stars and galaxies, to increase. This causes the light that leaves those objects to be stretched out as it travels through space. The key to understanding this is that light doesn't lose its energy because it's tired in the way we think of physical fatigue. Instead, it loses energy due to the expansion of space. This stretching of space causes the wavelengths of light to become longer, and as the wavelengths stretch, the frequency of the light decreases. This decrease in frequency means the light has less energy. The greater the distance the light travels, the more its energy decreases, and the more redshifted it becomes. The farther a galaxy is from us, the more its light is redshifted. This is why the light from distant galaxies appears redder than the light from nearby galaxies. The more redshifted the light, the less energy it has. This is a direct consequence of the expansion of the universe. The farther light travels, the more space it must move through, and the more it gets stretched out along the way. Interestingly, this effect is not just theoretical. It has real implications for our understanding of the universe. By studying the redshift of light from distant galaxies, astronomers can measure how far away those galaxies are and how fast they're moving away from us. Redshift has been crucial in proving that the universe is expanding and has allowed scientists to measure the rate of expansion over time. So, while it might seem like light is a perfect and unchanging entity, the truth is that it does lose energy as it travels through space. This is a result of the universe's expansion, which stretches the very fabric of space itself. Light isn't tired in the way we might imagine, but it does lose energy as it moves through the expanding cosmos, becoming redder and dimmer over time. Thank you for journeying through the mysteries of the universe with us. We've explored some of the most misunderstood aspects of space, time, and light. But there's still so much more to uncover. The universe is vast, and our understanding is constantly evolving. So, don't forget to look up at the stars and question everything you thought you knew. If you found these insights fascinating, consider subscribing to the Hollow Room for more thought-provoking explorations. We'll continue diving into the wonders of the universe, breaking down complex ideas, and, hopefully, making the cosmos just a little bit more understandable. Leave a comment below with your thoughts or questions. We'd love to hear what you think. And if you enjoyed the video, don't forget to hit the like button and share it with someone who would also appreciate the beauty of the universe. Together, we can keep learning, questioning, and exploring. Thank you for watching, and remember, the universe is always more fascinating when you keep looking deeper.